Happy New Year and welcome to the Afterword podcast's fourth season. It is so incredible to think we've been producing these episodes for 4 years. Who could have predicted that? Speaking of prediction, did you ever study the weather in school? I believe most elementary science programs have a unit on clouds. Now, I can't name any clouds, but interestingly enough, even in the late stages of dementia, my mother could still identify certain cloud formations in the sky. It must be something that really sticks with some people. Didn't stick with me, regrettably.
I personally am fascinated by weather and how it affects so many different parts of our lives. We certainly have come a long way in weather prediction, from folks licking their fingers to determine the direction of the wind to waiting around for groundhogs, and to see the measurement of caterpillar stripes in order to tell if it's going to be a rough winter.
Very true, Amy. And I, for one, am so glad we have experts in the field of weather prediction joining us to help us understand how the science of meteorology has changed over time.
Hi, I'm Holland Webb.
Hi, I'm Amy Boland.
And you're listening to The Afterword, a conversation about the future of words.
And we're happy to welcome to the Afterword table Dr. Chris Hennon, who is a professor at the University of North Carolina, Asheville.
And also we are here so thrilled to have Dr. Bill Martin. He is with the National Oceanic and Atmospheric Association. Welcome to you both.
Actually, both of you have fascinating personal stories. In just 60 seconds each, would you mind sharing the Cliff Notes version of your life and who you are?
Okay. You may think I have a fascinating life story, but I may surprise you and be boring, but we shall see. Actually, I grew up in Northern California and was always interested in weather when I was, in school there as an elementary student. I do reports. When we had a report to do, I'd find some weather thing to do. I went to college there, and none of the colleges I wanted to go to had meteorology programs, so I majored in mechanical engineering instead. And eventually got a master's degree in mechanical engineering. I did do, in mechanical engineering, there's an area called fluid mechanics that I sort of specialized in. And fluid mechanics has some degree of commonality with meteorology, especially in the numerical methods that they use. In fact, numerical methods for fluid mechanics developed side by side, essentially, with the numerical methods that were used in meteorology. So I had some background, and when I got my master's degree, I went to work for the Severe Storms Lab in Oklahoma, where they put me to work doing numerical modeling for about 5 years. And I eventually got my doctorate from the University of Oklahoma in meteorology and became a real meteorologist. After doing that, I went to work for the Weather Service. And my first job in the Weather Service as a science and operations officer was at the office in Glasgow, Montana, which is, they sometimes say it's too far north, the people who live there. It's up there. And it's the coldest place I ever lived. My personal record cold temperature I experienced there was 39 below one morning in February. And I had to get up before dawn and go to work, and, get your truck started and go up there. So I was there for a while. And after that, my second and current job was at the office in the Greenville-Spartanburg office. That's where I am currently.
That is fascinating. You have quite the varied background. Appreciate that. Well, Chris, how about you? What's your Cliff Notes version of your life?
Well, there's some similarities to Bill for sure. I grew up in Northern Ohio and about as far away from hurricanes as you can be, but I always had this fascination with weather and hurricanes when I was a kid, and I'd be watching the Weather Channel all the time whenever I got a chance. And I just always knew I wanted to do something in meteorology. But, like Bill, where I went to college, I went to Miami University in Ohio, and they didn't really have an atmospheric science or meteorology program. So I ended up majoring in aeronautics and mathematics. And when we took a lot of the same classes, I took a lot of the same classes that Bill did, fluid mechanics and things like that. I went on to get a master's degree at Purdue in atmospheric science, where I still was not able to study hurricanes. And after that, I got a job in the private sector. I worked for a company in the Boston area for a couple of years and working mostly computer coding. So I did some software engineering. But I wanted to go back to school, get my doctorate. So I went back to Ohio State. I finally got to study hurricanes. I got a position after my doctorate down in Miami, Florida at the National Hurricane Center, doing some applied research for forecasters down there. I got to do some forecasting of hurricanes when I was there. Great experience, but I realized I wanted to teach, and an opportunity came up for me to go to Asheville at the university there. And I took it. So I've been teaching weather to college kids for over 16 years now.
I love that. That's fascinating. Well, welcome to both of you. This is going to be a great conversation. Obviously, having these experts here helping us to dig into our very first theme for the 2022-23 season. Our fourth season is on weather. And so we're going to be talking a lot about weather in these first few episodes. So in order to level the playing field and help everyone feel a little more comfortable, you both have touched base with a few things already that I'm curious about. And we're going to just do a lightning round of vocabulary or phrases, and either one of you jump in and help us understand some of these terms. And the first one is numerical weather prediction. And both of you talked a little bit about that in your bios. So what is this?
Go ahead, Bill. You take the first one.
Okay, we can alternate. Numerical weather prediction is weather forecasting using a mathematical model, in almost all cases calculated by a computer. A mathematical model is, an example would be catching a baseball. Someone throws you a baseball, it goes up on an arc and comes down. We call that arc a parabola. And you can calculate the arc, actually, and predict where the baseball will land. Your mind does this automatically for you because it's a fairly simple thing you've seen dozens of times. And the atmosphere has more than just one baseball, has gazillions of things bouncing around and doing stuff, and they're more complicated, but we still use a mathematical model and use the computers to work out how all those parts interact.
Okay.
Yep.
Anything else to add to that, Chris?
No, he described it pretty well.
I love word pictures, so thanks for throwing the baseball analogy in there. That's awesome. Okay, next one, barometer or barometric pressure. I know we hear a lot about that, but I'm not sure people really understand what this is.
So atmospheric pressure is just the weight of the atmosphere. It's a force that is exerted on your body, on any object. And a barometer is just an instrument that measures that pressure. So any standard meteorological tower or down where Bill works, they have a series of instruments will contain a barometer. And barometers are important because they tell us, when the pressure is falling, when it's rising, and when it's falling. We might have poor weather coming. When it's rising, you're probably going to have fair weather coming. So it's a pretty standard meteorological instrument. It's been around for 200 or 300 years now.
Okay, excellent. Anything to add to that, Bill?
No, that was very good.
Okay. Well, and you kind of touched base with us. Another word we'll touch base with in just a minute. But what is a synoptic weather map?
A synoptic weather map, the word synoptic means to see together. And in a synoptic map, it's a map of some relatively large region like a state or a country. And you plot all the observations of weather on it at the same time. So you have a map of what the temperature was at 100 different places in the state of South Carolina, plot on that map at 2 p.m. on Saturday. That's a synoptic map. It shows everything together in one place. We tend to use synoptic maps to get a picture of the weather, and it's probably the oldest kind of map in meteorology is a synoptic map. Back when weather information was transported, by horseback, it could take months to get all these observations together because people, collected them and they sent along in the next month's mail or something. And then someone would plot them on a map and try to get them at the same time. It's possible to do a synoptic map months after the fact, if that's when you get the data. So it just has to be at the same time.
Gotcha. Okay. And Chris, you kind of touched base a little bit with us on this next one, atmospheric pressure, and now, but I'm going to add fronts. So what does that mean?
So in the atmosphere, we have what are called air masses, and air mass is like a very large area of air that has similar temperature and similar what we call moisture in the air, either dry air or moist air. And a front is just a boundary between those air masses. So when you hear a cold front, that's just a imaginary boundary in the atmosphere that's dividing an air mass that's warm and moist from an air mass that's cold and dry. So there's several different types of fronts depending on the types of air masses that they are intersecting, and also whether the front's moving or not.
Anything else to add to that, Bill?
Yeah, I would just add one thing about fronts. The word front itself dates back to World War I, and the meteorological concept of the front was copied from the military idea of a front, which was the boundary between two different armies. In particular, the Western Front in World War I divided Germany on one side and Britain and France on the other. And it was a very familiar concept to people at the time, and it was borrowed for use in meteorology to describe the boundary between air masses.
Can I use that in my classes, Bill? I didn't realize that.
That's fascinating. I love that. We're actually going to be talking about how how weather impacts history. So we'll have to bring that one up for our next episode. I love that. What about short range versus long range forecasting? I think I understand this, but let's divvy this one out a little bit.
Well, yeah, short range and long range, it's a matter of definition. For the weather service that I work for, we consider any forecast that's less than 3 days into the future as a short-term forecast. And anything beyond 3 days, we go out 7 days officially. So 3 days to 7 days is a long-range forecast. So it's typically, and that's for us. Now, if you were forecasting the climate, you might have a different definition. So you might want to forecast the climate 10 years from now might be short range, 100 years from now might be long range. But for weather, what we do, it's 3 days is kind of the dividing line. It could be something else, but that's what we use.
Okay. Is there more accuracy between one or the other?
Oh, yeah, definitely. The longer the forecast into the future, the less accurate it is. I think I ask people about this occasionally when I talk to the public, and this seems to be pretty well understood by the public. But I would tell you that it's not obvious. In fact, the people who did the first numerical weather forecasts had it in their mind that they will be able to forecast the weather any distance into the future they wanted to. Turns out not to be the case. And nowadays it's considered almost obvious that the further in the future your forecast is, the less accurate it is. And that's absolutely true and an important point. So
yeah. Okay. How about you, Chris? Anything else to add?
Yeah, I mean, basically, if you're trying to forecast things like specific high and low temperatures and the such, if you go beyond 7 or 8 days, you have essentially no skill in doing that. So there's definitely a limit.
There you go. Okay. Well, I know I feel a little bit more educated about these terms. And so now let's get into a few more questions and think about weather and how it's changed over time.
How would you explain how weather prediction has changed over time? Do you have a favorite moment or breakthrough that you think launched meteorology into the science that we know it as today?
Sure. I mean, we've known how to predict the weather essentially, as far as I know, since the early 20th century, and we've been trying to do it since World War I. The problem that with predicting the weather early on was we kind of knew how to do it, but we didn't really have the tools to do it. We have these physical relationships that describe how the atmosphere works, but we had to solve these relationships by hand. And it just wasn't feasible to do. Now, probably the biggest thing, in my opinion, and Bill may have something bigger in mind, but the invention of the computer after World War II allowed meteorologists and other scientists to start solving these equations much more quickly. And so we were able to take the information that we gathered from the atmosphere, feed that into these computers, and then the computers would be able to produce a forecast in a reasonable amount of time. Now, early on, the forecasts really weren't that great for a variety of reasons. But as we've as computers have become faster, more efficient, and we become better at observing the atmosphere, the forecasts are continuing to get better and better and better even today. So I think that the advent of the computer age was really a key moment for weather prediction for sure.
Okay. I'm hearing the need for tools, and a computer would be a good tool. How about you, Bill?
I said there's at least two things that are essential to numerical forecasting, and which is the main kind of forecasting we do nowadays. And Chris mentioned that going back to World War II, in fact, 1918 was the first time someone tried to actually do a numerical weather forecast. He did it all by hand, took a month to do the calculations. It wasn't practical. It didn't work. He published it anyway. And the concept was out there for decades. People knew about it. It wasn't practical. It was interesting. And then during World War II, they built the world's first digital computer, which could calculate things 1,000 times faster than anything that had come before. That computer was called the ENIAC computer. And the people who built it had one of the things that it was built for the military to calculate ballistic firing tables, but they also built into it enough memory that it could also do problems in hydrodynamics, including meteorology. In 1946, that computer was declassified, and they immediately got money to fund the world's first numerical weather forecast, which was run on that computer. So as soon as computers became a reality, the idea that was implanted from the guy named Richardson who did the world's first numerical weather forecast in 1918, that idea was there. And that as soon as the computer came that could actually do it in a practical manner, it became a reality almost immediately. It was one of the very first applications of computers was meteorology. So that was a key element, was the creation of that computer.
Wow. That is fascinating to think that someone did this by hand in 1918.
Yes.
And his math was solid, but he needed the speed. Wow.
He had the idea that you could do this manually to get hundreds of people together doing calculations simultaneously. It would be practical, but it's just too expensive, and no one did anything like that. And then they built a computer that could do the work of 10,000 people and problem solve. So,
how about that? Amazing.
Yeah.
All right. So, what is the most difficult aspect of weather prediction? And do you have a story when you got it right or wrong? And Bill, I'm going to toss that to you first.
Yeah. The most difficult aspects of weather prediction are certain things that could go either way. A good example is freezing rain. Freezing rain requires a very specific temperature structure to the atmosphere. And if that forecast is off a little bit, it could go from freezing rain to rain. Freezing rain has huge impacts, shuts down cities. Rain has very little impacts. It's usually a good thing. Or you could get snow, which has some impacts, but they're not as bad as freezing rain. And it's possible for an error in the forecast of a degree or even less can make the difference there between, freezing rain and rain. And you can't, even now, we can't be that precise all the time. So things like that. And there's always going to be some things that are just too close to call, no matter how good our models or how good our understanding the atmosphere. If you want a personal story of forecasting, when I was a graduate student, I worked in the mobile radar teams, and we would have these trucks with radars on them. We drive them around. I was actually forecasting for them. And after one long day trying to find tornadoes and not succeeding, they wanted to forecast for the next day. And there I am in the back of the radar truck. Hadn't looked at a map all day. And I had no idea, but I called back to the office and asked them to read me the surface observations of different locations. So they told me, the wind direction, temperature at half a dozen cities. And I mentally sort of put together a picture in my mind of where the front was and what was probably going on in the upper atmosphere. And I made a forecast based on that, and it actually turned out pretty good. I consider that my best forecast because it was done, in the back of a radar truck going down Highway 41. So
there you go.
Yeah.
Wow. Well done, you. Did you ever see a tornado?
Yeah, we eventually did get tornadoes.
Okay.
In that project, I saw quite a few, actually. So it was worth my time.
Okay. Excellent. How about you, Chris?
I got a couple of forecast stories. When I first came to my university here in Nashville, we're in the mountains in the southeast, and it's notoriously difficult. Bill knows all about this, trying to forecast winter storms in the mountains. For part of the reason he mentioned, just a small change in temperature can really affect like how much snow you get. And I was in a big faculty meeting, and we were talking about commencement in December, and the president of the university was talking about when to show up, and there was a big winter storm in the forecast. And I raised my hand in front of a couple hundred people, and I was a brand new faculty member, and just said, "Oh, we're not going to have commencement." And everybody would turn to me like, "Who's this young punk, saying that we're not going to have commencement?" And fortunately, I turned out to be right. And we did get 14 inches of snow and there was no commencement. So that was a good moment for me. A bad moment was when I was forecasting at the National Hurricane Center. And I'm not a professional forecaster by any means, but they let me do some forecasts for some hurricanes. And at the time, I did a lot of radio interviews. And I was on the phone with Jamaica, radio station in Jamaica, and Hurricane Ivan in 2004 was heading right towards the island. It was a big, massive Category 4, which is a really strong hurricane, or Category 5 even, if I remember. And I basically told the entire island of Jamaica that they were going to basically be destroyed because all the computer models were having the hurricane go right over the island. And the storm at the last minute basically took a sharp left-hand turn and went around the island, and the island avoided the worst of the hurricane, thank God. But I always make a joke now that I'm not allowed back on the island in my pictures on the wall in the airport because I caused a bunch of fear and chaos. So that's not my proudest moment.
There you go. I love that you have a high, one of the highest peaks and a low. Those are
yes. Anybody who forecasts the weather will have those peaks and valleys. Guaranteed.
There you go. Okay. Well, this is excellent. I love these stories. Thank you for sharing them.
Are there opportunities for you to collaborate with other scientists in other disciplines? How do those crossover networks help support what you do as well as enhance other fields?
Yeah, sure. I'm obviously in the business of educating students and giving students experiences, research experiences. So a lot of my connections have to do with that, finding students opportunities. I do some research. Most of my research, of course, has been in tropical cyclones, but I've done some research in using satellite data in various forecasting applications. So I've been working with people at in Asheville. There's a climate center called the National Centers for Environmental Information. And I've worked with some people there on some projects having to do with hurricanes and also climate as well. I work with statisticians because lots of data and weather prediction and meteorology, and I'm not a statistician, so I need their help to help me make sense of the data that I work with. And climatologists I mentioned, and even some computer scientists. These are people who can use computer code to tell the computer to do things I want it to do. And even though I know how to do some of that, I really need help in programming these computers so that I can see the things I want to see. So in my life, those are the primary people that I collaborate with.
That's excellent. And I'm sure that they benefit from your knowledge as well.
For sure. It's definitely a nice ecosystem, mutually beneficial. Yeah.
Yeah. Very good. Okay. How about you, Bill?
There's almost always some commonality between what we do in meteorology and other fields. For example, I mentioned I got my master's degree in mechanical engineering, and I did my thesis on cardiac Doppler ultrasound, and the hardware they built did Doppler flow mapping, where they put a transducer on your chest and would get an image of flow in your heart, and red colors would be flow towards the transducer and green would be flow away from the transducer. I found out later that they copied that from Doppler radar use in meteorology, where we have a radar trying to image a thunderstorm, and red is flow towards the radar and blue is flow away from the radar. And if you get red and blue right next to each other, that's possibly a tornado. That was directly copied for use in Doppler ultrasound. And when I went to the severe storage lab to interview for my first job there, I showed them my thesis work with Doppler ultrasound with color flow mapping pictures, and they were very interested because that's exactly the same thing they did. Mathematics were identical. The technology was similar in almost every level. So there's lots of examples of that. That's just one. But as Chris mentioned, math, technology, even biology enters into our field in some ways at times. So, and we both benefit from that crossover.
I love that. That's fascinating. Just so important in that collaboration. Thank you. Well, we're going to wrap up our first part of this conversation because we do have several other questions that we'd like to ask you. But we'd like to know, first of all, what is an essential element we need to understand about the stories and weather prediction, how it's changed? What is something that's essential? And Bill, what do you think? What's an essential element?
Yeah, I would say that I want to avoid overselling numerical forecast models. That is our primary tool nowadays in forecasting the weather very far into the future. And our forecasts are dramatically more accurate because of it. But it's not the whole story. We still have a lot of experience we bring to bear in interpreting those models and second guessing them and applying them. What does this mean in everyday terms? There's a lot of things the models don't do. There's some things they still get wrong. They aren't perfect. And we still need people to interpret a lot of this data. I think it's important to keep that in mind. I mean, 50 years ago, we had no computers and we only had experience. And forecasts were often not very good because of it, but they weren't worthless either. We had good forecasts maybe a day or two into the future. Now we got really good forecasts, 2 to 5 days is often not bad because we have computers. But computers plus people are better than computers alone.
Okay, I love that. That's a great essential element. Thank you. How about you, Chris?
I would just say forecasting the weather is difficult, but we're getting better and better at it. And we're right most of the time. You always hear about the times where the forecast is off or we blow the forecast, but many people don't realize how good we're getting at it and how right on the forecast is most of the time. So I think that's something people should realize.
Absolutely. Absolutely. Celebrate what's right, not just focus on the negative.
Right.
Like that. Excellent.
Sure.
These are so good.
Special thanks to Chris Hennon and Bill Martin. This conversation has been truly enlightening. While you wait for part 2, please go to theafterwordpodcast.com and become a subscriber. Leave us a review and tell your friends about us. And as always, you are welcome at our table.